Hey, welcome back to your favorite intermediate algebra class. We're going to talk about and perform operations with complex numbers. So we're going to expand your numbering system. So let's talk about some complex numbers for a minute. Let's say we had a quadratic of the form x squared plus 1 equals 0. And mathematicians looked at this previously and they went to solve this thing and they're like, wait a minute, there is no real solution for which x squared equals -1. They'd go to square root and they're like, wait, I can't take the square root of a negative number. So what they did is they called this number right here, the square root of -1, they gave it a name. They said, we're going to call this the imaginary unit, the square root of -1. So that stuff like this is now solvable. Okay, so the imaginary unit, is the square root of -1. It's kind of poorly named, the imaginary unit, because it's not imaginary. It actually exists in real life. If any of you ever go into like electrical engineering and so on, they're in your circuits all over. You'll work if you ever work in that industry, you'll see the imaginary numbers all the time. Okay, so if I is the square root of -1, if we square that, that would undo it. So I squared is -1. Okay, so if I is the square root of -1, I squared must be -1. So anything of the form a plus bi, where a and b are real numbers, is called a complex number. It's called a complex number. Okay, so for instance, I is a complex number, just the old I. Okay, 2 plus 3i is a complex number. Negative 4i is a complex number. Okay, all these are complex numbers. So let's look at the big picture here. We have our natural numbers, 1, 2, 3, and so on. We have our whole numbers, 0, 1, 2, 3. We have our integers, that funky looking z right there, all our integers. We have our rational numbers, so anything of the form uh, p over q, or p and q are integers. Okay, so it has to be able to be written as a fraction, 3/7, -1/3. Now these rational numbers in decimal form either terminate, like 0.6, 6/10, 3/5, or they repeat, like 1/3, 0.3 repeated. Okay, so that's your natural numbers, your whole numbers, your integers, and your rational numbers. Now you have irrational numbers. The most famous irrational number, of course, is pi. And then all of these are encompassed, the set of rationals and real numbers, we all called these real numbers. Okay, so you've been existing in this real number world, and now we've just expanded it with the imaginary unit I. Okay, anything of the form bi, where b is a real number, is an imaginary number. Okay, and the combination of these two, I guess you could say, so all real numbers and imaginary numbers are complex numbers. So all of these can be written as complex numbers. Okay, so for instance, if you take the real number 3, how is 3 a complex number? How can I write 3 in the form a plus bi, where a and b are real numbers? You say, well, that's easy. I could just write it as 3 plus 0i. We just never wrote the 0i before. Okay, so 3 is a complex number. So every real number is a complex number. Every imaginary number is a complex number. So for instance, this 3i over here, how do you write 3i in the form a plus bi? You say, well, that's 0 plus 3i. Okay, so everything now can be written as a complex number. Complex number. So let's simplify some of these here and put it in its standard notation here. And what you want to remember is I is the square root of -1. Okay, so anytime when you're breaking these down, I like to think about it. I'm going to use that product property. I say, well, -1 times 9 is -9. What's the square root of -1? And you can even split that up if you want to. Well, the square root of -1 is I. What's the square root of 9? 3. So this is 3i. The square root of -9 is 3i. How about square root of -16? I say, oh, that's 1 times 16. The square root of -1 is I. Square root of 16 is 4. This is 4i. How about the square root of -12? Well, that's -1 times 4 times 3. I, 2, 2i root 3. Root 3 is left over, and it just stays underneath the radical. Okay, so now we can solve things like this here. 2x squared plus 3 is negative 15. I go ahead and I subtract 3. Solve this team. 2x squared equals negative 18. I divide both sides by 2. I get x squared is negative 9. I go ahead and square root it just like we did before. X is plus or minus, and then I just simplify this. This is negative 1 times 9. Square root of negative 1 is I. Square root of 9 is 3. So this is plus or minus 3i. Plus or minus 3i. Okay, so that's our solution. In other words, if I was to plug in 3i and check it, or negative 3i, they should satisfy the original equation. So let's check this. Does 3i really work? Let's subtract 3. Well, you know what? Let me not do that. What am I doing? Let's go ahead and we take the 2, we multiply by 3 squared I squared. 3 is squared, I is squared. 3 squared, 9. What's I squared? If you remember, I was the square root of negative 1. I squared should be replaced with negative 1, because if I square that, I undo it. So I squared is replaced with negative 1. So times negative 1 there. So I got 2 times 9 times negative 1, negative 9. Negative 18 plus 3 really is negative 15. Look at that. It works out. And you could check negative 3i as well. But let's go down. Let's solve this next one here. So 5x squared is a negative 10. I go ahead and divide both sides by that 5. Oops. By 5, I got negative 2 square root plus or minus. I'm going to write this as negative 1 times 2. Square root of negative 1 is I. I'm left over with the 2. So plus or minus I root 2 is my solution on that. Okay. Let's add and subtract complex numbers now. And you're kind of treating this I kind of like a variable, if you will. In other words, you're combining like terms. Go ahead and distribute that negative there. So combine like terms. I say, well, 5 is a real number, minus 1, that's another real number. 5 minus 1 is 4. And I got a positive I plus 2i. So 1i plus 2i is a 3i. You always want to write these in the form a plus bi at the end, right? 4 plus 3i in this case. Okay, down here we go ahead and we distribute that, distribute the plus. Oops, that's a minus there. Minus 8i plus 5 minus 6i. 3 minus 7, negative 4 plus 5 is 1. Negative 8i minus 6i minus 14i. Again, combine like terms. Okay. All right, how about multiplying? So we're going to go ahead and FOIL this. 1 times 3 is 3. 1 times the 5i, 5i. Negative 4i times 3, negative 12i. Negative 4i times a 5i is a negative 20i squared. As soon as you see an I squared, you got to make that replacement with negative 1. Okay, now we combine like terms. So 5i minus 12i, negative 7i. And again, we make that replacement with negative 1. So we got 3 plus 20. Negative 20 times negative 1 is positive 20. So 3 plus 20, 23 minus 7i. Okay. Over here, you got 4 minus 5i. Now you notice these, the only difference between these two is this one's a minus, whereas this one's a plus. These are called complex conjugates. The only difference between the two is the sign in the middle. So like if somebody asked you, what's the complex conjugate of 3 minus 2i? You'd say, well, the complex conjugate is 3 plus 2i. What's the complex conjugate of negative 4 plus 7i? And you'd say, well, the complex conjugate is negative 4 minus 7i. So you're only changing the sign between them to find a conjugate there, okay? Let's see what happens when we multiply these complex conjugates. First, 16. Outer, positive 20i. Inner, negative 20i. Last, negative 5 times positive 5, negative 25. I times I squared. I squared is negative 1. 16 plus 20i minus 20i, so those are gone. Minus 25 times a negative 1. So 16 plus 25, 41. Hey, what happens here? We end up with a real number. So when you're multiplying two conjugates, you end up with a real number. Now that plays into division, because in division, again, we want to simplify this so it looks like a plus bi. And the problem is I'm like, hey, I don't want any i's on the bottom here, if you will, right? So what am I going to multiply this by? Well, I'm going to multiply by the conjugate. But I got to do it to the top too. I can't just all of a sudden introduce it, because 1 minus I over 1 minus I is 1. I'm multiplying this by 1. So what you do in this division is you want to multiply by the complex conjugate of your denominator. Okay? And then you just go ahead and you FOIL this thing, and then you simplify. Simplify this thing down. So first outer inner last, 6 times 1, 6. 6 times the negative I, negative 6i. Negative 4i times 1, negative 4i. Negative 4i times the negative I is a positive 4i squared. Don't forget I squared is negative 1. Okay. Down here we go ahead and do that. Okay. Notice those are canceling there, right? So on the bottom, in fact, let's do the bottom. 1 minus, and here's your I squared. That's negative 1. So on the bottom, it looks like we got 1 plus 1, 2. Okay. Let's do the top, this numerator here. Negative 6i minus 4i. Negative 10i. We got a plus 4 times that I squared, negative 1. So 6 minus 4, 2 minus 10i. Okay, we go ahead and simplify this again. We're trying to get it like this, a plus bi. You notice this is not in the form yet. But this 2 is a common denominator of both of those. So I write 2 over 2 minus 10 over 2i. 1 minus 5i. 1 minus 5i. You're welcome to try this one as well. You can pause it and try it before I do it. We're going to go ahead and multiply by the complex conjugate. 2 plus I. 2 plus I. Go ahead and first outer inner last this thing. To the bottom there. Make the replacements and combine like terms. Replacement of I squared, which is negative 1. So 6 minus 2 here, 4 plus 7i. On the bottom, it looks like we got 4 plus 1, so 5. So 4 fifths plus 7 fifths I is your solution on that one. Okay, you can also graph these things. When you're plotting a complex number, what you do is you take the real axis, the horizontal axis is a real number. And then your vertical axis is your imaginary portion of the complex number. Okay, so for instance, let's do 2 plus 3i. Yeah, I do this part on the horizontal axis, so I go over 2, and then I do the 3i piece, so positive 3, 1, 2, 3, positive 3 piece on the vertical axis. So there's 2 plus 3i. So it's just like graphing 2 comma 3. Part B there, negative 1 plus 2i. So I'm going to do the negative 1 piece first, negative 1, and then I go up to plus 2i. That is negative 1 plus 2i. So it's exactly like graphing negative 1 comma 2 on a Cartesian coordinate system. Now this 4, I see a lot of errors with this one. This 4, think about a plus bi, a plus bi. Well, what is this? 4 plus 0i. That's the exact same thing, right? So put it in the complex form if you need to, and then graph it. 1, 2, 3, 4. There is 4 plus 0i, or 4. What about the negative 3i part? How do you write that as a complex number? You know, well, 0 minus 3i, right? So go 0 in the horizontal direction, then go down 3. There is 0 minus 3i, or negative 3i. Okay, let's do one more here. How about, negative 2 minus I. So I go negative 2 horizontally, left 2, down 1. There's negative 2 minus I. Okay. All right, make sure you guys bring any questions you got to class. Thank you.